Today, my point of discussion is we'll be starting with LU decomposition. Then we'll go to some other topics of Gauss-Seidel technique. Actually, your decomposition technique is nothing but it will facilitate some calculation when you are solving system using linear algebra. In your LU decomposition, actually L represent the lower triangular matrix and U is your upper triangular matrix. In your Gauss-Seidel elimination, in Gauss's elimination, what we have done, we simply eliminate the variable in such a way that your coefficient matrix will take the form of an upper triangular matrix, and then we use back substitution to find the solution of your system. Even you can convert from a lower to upper, just and your matrix become your lower triangular one. So the same method that we applied there in the elimination process can be implemented here to decompose your matrix into two components, L and U. Then what is the benefit we will be obtaining by decomposition the matrix into L and U that I am highlighting? Then we will be going to the text. Okay. Our system of equation is this that we have learned. Okay, we have a coefficient matrix. Then your variable or unknown that you need to determine. This is your known side. Okay. What we usually do, if this matrix can be decomposed into two matrices, say L, U, then we can rewrite this equation in this way. That this intermediate operation, let us write it, U x is equal to, say, matrix D. Then this equation can be written as L matrix D is equal to B. Isn't it? Then what can you do? Your D is, for example, an intermediate column metric that you need to determine. Then from where to start then? If your A matrix is given, if that from that A matrix, if L and U matrices could be calculated, then you can solve this equation first. No, you can solve this equation first because in this case, your B will be known to you. Then your L is already with you by decomposition, decomposing your matrix A. Then you can solve for D. Your D will be available from this equation. Once your D is there, then you can use D here is solve for X. Okay. That's it. What is the advantage of this technique? Actually, the thing is that in many of our electrical engineering problems, we have to solve our network repeatedly or solve our problem repeatedly, keeping our input constant. In this context, I want to ask you a question. That when you learned your circuit, electrical engineering circuit, first year, you have been introduced with Thevenin's theorem and Norton's theorem. Can anyone tell me why we need these two theorems? Is there anybody in your group who can answer this question? Hey, can you hear me?
Yes, sir, we can.
If you can hear me, probably you heard my question. Okay. If you can answer, then say your answer. If you can say no. You have to have some response. Okay, so that I will understand that you are engaged. You don't have any idea.
No, sir.
No idea. Then now you tell me you are probably in the third year. Of course, you are in the third year at the courses you are learning. So how many semesters you spent there? 5 semesters, 4. So then what is the outcome of your learning there? You invested huge amount of money and time. What is the outcome? Can you, for example, if you want to do a business, you have to invest money and out of that investment, you need some return. So what is your return? The reason is that you did not invest your money. Either your guardian or some other person invested it. For this reason, you don't have any significance of time with you. Be careful about that, okay? But ultimately, you have to know this. No, there is no anybody in this group who can answer at least one benefit of using Thevenin's theorem. I asked the same question to section A. Two student answers nicely. So try to learn something about by your own. That if you do not feel importance of learning by your own, no matter to what extent your teacher will force you, you will never wake up. Try to wake up. So once this thing is with us, we'll find some benefit of solving practical problem where a repeated solution is needed. That repetition of the solution only is due to the change of input variable. You do not, your coefficient or parameters of your system will be remaining unchanged. So if this is the case, then if you can have something that will be remaining constant throughout our exploration, then this decomposition technique will help you that if a matrix is with us, it can be decomposed into L and U. Then for any value of B that is reasonable, we can easily solve for our unknowns. We need not to calculate A or solve the whole process by repeating the decomposition for a changing value of B. So this is what our decomposition technique. Then how to do that? Your technique is very simple. Okay, I'm showing it. Those things are there in your text. You can have a look. It is in chapter 10. Okay, what I am going to discuss, it is article 10.1.1, and we'll be illustrating the thing how we can do that for a 3x3 matrices. We have our algorithm there. Computer can do it for you, but in hand calculation, you know that we have some limitations to proceed, but that will be remaining with us when we are solving our problem by hand. So if we have a 3x3 system, then your coefficient matrix is A11, A12, A13, A22, A21, A22, A23, A31, A32, A33. In what ways we actually converted our matrix into upper triangular? We multiplied our first column by a factor. That factor was equal to A21 divided by A11, isn't it?
Yes, sir.
And then the resulting column is subtracted from the second column. Second row, resulting row is subtracted from the second row so that the first variable will be eliminated, isn't it?
Yes, sir.
In that operation, you see that we'll have, I am not repeating the thing because you have the thing with you in your earlier classes. So you just repeat the thing, Gauss's elimination procedure. In that case, it will become 0. And a new A22 constant will be there, and a new 23 constant will be there. And similarly, you can replace your this variable here. In that case, your multiplier will be equal to A31 divided by A11. Okay, then it will be equal to 32 prime. Say it is equal to A33 prime. This is the first stage of your elimination. Second stage is what? You have to eliminate the second variable from your second row, the modified second row. In that case, your multiplier can be something like this, A32 divided by A22 prime. If you have this thing with you, you multiply this second row, modified second row with this multiplier, and you subtract this with equation with the new third row. Then what will happen? This will be eliminated. Eventually, you will be obtaining a matrix. That matrix is a triangular matrix. It will also be 0. And say we will be obtaining another coefficient there. This will be equal to A33 prime. So this is your upper triangular matrix. Okay, U. Now, how to find your A? Actually, L can be determined very simply that if we designate this quantity, for example, this factor that we determined earlier as equal to say F21, and we are designating this factor as F31 and this factor as F32, then we can form a matrix now with something like this. Okay, this is your in the first place, your A11 will be there. Your total matrix then will be equal to, you can have an L matrix. That L matrix will be equal to, in the diagonal, it will be equal to 1, 1. In the off diagonal elements in the lower side would be equal to F21, and that will be equal to F32. This will be F31, and this will be, this is not F3, this is F31. So it will be equal to F31, this is your F32. What is important is that in LU decomposition, and you can easily verify that if we using these two matrices, you can easily generate Ure matrix. Now, it is important is that in determining, for example, in decomposing your matrix A, you need not to, for example, calculate many things. The way you are converting your matrix into upper triangular by using Gauss elimination, in the elimination process, you simply retain this factor that you have used for elimination. Then you insert the factors here, and with the diagonal elements is equal to 1, 1, 1. This is your A. L. If this L and U is with you, then what you can do, you can start you solving your problem, that you have your L, you have your U, you have your X equal to B. I am not just avoiding the symbol. Okay, this is what we call represented by D. Then we have our matrix LD is equal to B. Then you solve for D. This is at the first stage. Then when your D is available, then you have your UX is equal to D. Then your X will be available with us. Okay. Let us use an example there just to get accustomed with the process. The general algorithm is available with you. You can look at this algorithm. Okay, this is example 10.2 from your text. You can easily get a problem from an electrical circuit, from an electrical machine, from your power system, and you can apply this technique there. We'll be showing few things later. Okay. So, it is in chapter. Okay, this is your problem that we have solved for by using Gaussian elimination earlier. Now, if we want to transfer this matrix into L and U, what you need to do, you have to first convert this matrix. You have to convert this matrix into what matrix? In order to proceed.
Sir, your screen is not visible, sir.
Sorry?
Sir, your screen is not visible.
It is the problem of all the students or you only? Is there anybody who cannot see this screen?
Sir, visible, sir. It's visible for me.
If someone is seeing it, then others are not. This is the problem from your end. Okay, you solve it. But if no one can see it, then this could be the problem from my side, okay? Because I cannot resolve it. If you have your problem, you can restart it and rejoin. Okay, then hopefully you can see it. Now your problem improved.
Sir, I will rejoin.
Sorry,
Sir, আমি rejoin করতেছি স্যার।
রিজয়েন করে দেখো বাবা, কারণ আমার এখান থেকে তো অন্যরা দেখতে পাচ্ছে, তাই না?
জি স্যার, জি স্যার।
Is it okay now?
জি স্যার।
So that is what the thing, okay? If all will be claiming that they are not seeing it, only when I can explore the problem from my end, okay? Similarly, what I have seen that some students are saying that this problem happened, but others are not. This is the problem from your side, okay? Either your network could have a problem or your browser can have a problem, okay? If you have your personal computer, try to be updated always with your browser settings. If your Chrome will not work, then you can use Edge. Okay, then hopefully you can see it. Now this is your problem, okay? We have solved this problem earlier, didn't we? Okay, let me see it. There could be a problem, for example, okay? Actually, I don't know, how did you see the screen earlier? Actually, I was sharing the other screen. Now it is okay?
হ্যাঁ স্যার, এই যে এখন বইটা দেখা যাচ্ছে, এখন ইয়েটা দেখা যাচ্ছে।
The previously probably you are seeing the whiteboard, okay?
Yes sir.
Okay, sorry, actually I was that screen was not shared actually. But I don't know why the others were saying that we are seeing it. I don't know. Okay, I was misguided. Sorry. So this is your problem. Okay, didn't we solve the problem earlier by using Gaussian elimination? So in your LU decomposition, actually, the first step is same as the Gaussian elimination. So when we use Gaussian elimination, we used successively we eliminated the variable from the second and third equation. Then we got a matrix. This matrix is actually what? Is it not your U? Upper triangular? Is it?
Yes sir.
If it is U, then our object, while doing U, you see that this part is not same as B, because it has been changed to some other matrix, isn't it? Because of this row and column operations. Now our U is available with us. Then what we can do, while calculating U, we have had some factor, isn't it? First factor was 0.1 divided by 3, isn't it? And the next factor was 0.3 divided by 3, isn't it? And that is equal to your this element, and this is equal to your this element. Next thing is, we have to calculate, after having this thing done, next we divided the modified coefficient of A3 2 prime by the third element there in your what we call L matrix. So your L matrix, you did not to calculate separately. While converting you can retain the multiplier that you used, and you placed your multiplier in the appropriate locations. Then you set your diagonal equal to 1 1 1. Then this is equal to L. Okay, this matrix is equal to now this is your matrix, this is your L. So then just we know that your LD is equal to modified B, LD is equal to not modified B, actual B. So if your LD is equal to B, and you see that your L is a triangular matrix, then you can easily use your substitution. But in this case, Your substitution will be forward or backward. Okay, what is the value of D1? Is not your D1 equal to 0.85?
Yes, sir.
You have to multiply this column matrix with this row matrix to find and sum them to find the first element D1. And your D2 would be equal to what? 0.003333 multiplied by D1. No, the next element will, next equation will be equal to what? Next equation is equal to 0.03333 into D1 plus D2 is
Equals to
equal
minus
to
19.
minus 19.3, isn't it?
Yes, sir.
Then you can solve D1. Then and similarly, you write your third equation, okay? You multiply this row with this column. Here in this case, D1 is already with you, D2 is with you, then you can solve for D3, okay? Once you D1, D3 and D1, so D3 is available to you, then you will have another set of equation by using your upper, what we call upper triangular matrix to find the resulting solution, okay? Then your D will be there. Then you can use your upper triangular matrix here to solve for the problem. Your X equal to 3, 2.67, okay? So in this way, your upper triangular matrix ALU decomposition is done. Now, what is the advantage of this thing that I have already touched? That if we have, because in most of the cases, you see, if you want to solve an equation, that equation is homogeneous type. For example, say, if we have an equation, that equation is equal to something like this. It is disconnected. Am I connected?
Yes, sir.
Can you see the screen?
Yes, sir.
স্যার ওই যে বই খুলে রাখছেন স্যার ওই স্ক্রিনটা ভিজিবল
আর সেটাই তো আমি দেখাইছি তোমাদেরকে।
আচ্ছা স্যার
Okay. For example, if we have an equation, that equation is say just writing for two variable cases. Okay, a22, a12, x2 equal to 0, a21 x1 plus a22 x2 equal to 0. What is the solution of this equation? Can you tell me what will be the value of x1 and x2 for any values of a1, a2? Okay. Actually, the thing is that this is very similar to the problem. If you have a circuit, that circuit contains a resistance, something like this, a two loop. So this is R1, this is R2, this is R3, this is R4, this is R5. You have your loop equivalent current I1, you have your loop current your I2. What is the value of I1 equal to what? I2 equal to what? If you cannot respond, then how can I find interest in just advancing with this lecture? Hey, what will be the value of I1 and I2? No one can answer it. Hey, common sense, can you apply your common sense there to answer this question? Probably I have to stop, for example, giving lecture. Because I cannot teach a specific cohort of students in this way. I am keep going, speaking there, but you people said they are doing nothing. Hey, is there anybody among you who can answer this question? What is the current of this circuit? I hope a student of class 10 could answer it.
স্যার ইকুয়েশনটা বলবো?
Equation
I1
বলবে
is
কেন? I want to know the answer. তোমাকে ইকুয়েশন ড্রাইভ করতে আমি বলি নাই। I want to know the answer that this is a network. All resistors are connected in this way. And you have your two loops there, I1 and I2. What will be the current I1 and I2? In order to generate current, can current be produced in a resistance by itself?
So it will be 0, I1 and I2 equals 0.
That means you are taking 5 to 10 minutes to answer this question. That this question can be answered by a class 10 student probably who have been introduced with the behavior of a simple electrical circuit. So you can easily identify or measure that what you have learned throughout your last 3-4 semesters. You can, for example, give me many reasons that due to that and this and this and these reasons, numerous reasons that that you are not responsible, your teacher is responsible, your system is responsible, etc., etc., etc. But that will not change your fate. Be careful about that. Nobody will come to accuse your teacher. Rather, the consequences of your misunderstanding will be with you, and you have to bear the consequences of this thing. Okay, this type of homogeneous equation in passive network has no meaning, because you need a source to generate a current in a resistive network. And eventually that source will be coming into the right side of your matrix equation. So what it happens that in a practical problem where you are using your matrix algebra to solve it, you will see that the B matrix is the source matrix. Okay, if you have your sources there, that is will be included in B. So if you change the setting of the source, then you will have a new set of currents, and those new set of currents you need to solve again. Although the coefficient of the parameter values of the electrical circuit, passive parameter values of the electrical circuits, it did not change. So if you use this LU decomposition technique, you have decomposition L and U, that L and U will be remaining same for any values of any justifiable values of B. So you can simply use this technique to solve it readily, other than going from the top, like your Thevenin's theorem, that if you have a complicated network, you can replace this network by a simple electrical circuit like a voltage source or a current source. Then whatever change you made in your load side, that will not affect, for example, the parameter values of your network side, so that you can easily change the value of the load and calculate power current flow just associated with the load, just by solving a simple RC type network or something like this. And I was expecting that this was the content, most important and interesting content that you learned in your first year. Okay, no problem. Still you have time to proceed with, try to do that. The algorithm is there, try to do it. Okay, another version of this. Okay, this classical version of your LU decomposition is termed as Doolittle decomposition. We have another decomposition there. This is the crowd decomposition. In this case, the difference is that the diagonal 1, 1, 1 is associated with the U matrix. And you can form your L matrix in the way that is described in the general form in 10.7 and 10.1. Okay, try to apply this thing in the example to get accustomed to this process. Now these things are there with you. You know this thing, how to invert the matrix. I will not be touching this thing here. Now I will be going to what we call further discussion of your what we call Gauss-Seidel technique, because this is the most important and widely used method in engineering for solving many types of problems. Another issue is that you are doing probably lab. I don't know what you are doing in the lab. The method that you are using, you have to implement there in programming. You can solve it. Apart from our MATLAB environment, You can also use your other software environment. For example, your Microsoft Excel can be used to invert matrix to solve a linear system of equations. You can have a look there. You see that your MATLAB has already algorithm developed in it, but your task is not that you have to use this thing. Your task is you just program by yourself, just to try to know the consequences of the thing that we have discussed earlier. Okay, now I am talking further about your Gauss-Seidel method. You see that in our engineering problem, at the beginning of the chapter, you will find some example that in our engineering learning, you see that we have our system of equation that we frequently handle, just trying to just give an idea about it by using whiteboard. Okay, we know that if we have, in most of the cases, our engineering system will generate, for example, our simultaneous equation. Those simultaneous equation has some nature, okay? For example, say we have a voltage source there, and we are getting, for example, something like this. Say this is a or you can consider another resistor there. You can say R1, R2, R3, say this is R. Hey, can you hear me now? Because the network was disconnected. Yes, can you hear me?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, I was discussing about our engineering problem. Okay, if we have a system, for example, a resistive type network, something like this. How many loops are there?
Sir, 3.
Okay, look, some of you are probably thinking that this is the thing that why we should discuss about it. You see, it is not something like that. You need a very big problem to understand the basic feature of your numerical technique, okay? You can study it by your own your problem, okay? I don't know, because I actually try to instill it to my students so that they can set their problem by their own and they can solve it. Unless you can set your problem, you'll never learn. Finding a problem is more important than solving it. Okay, then you see, tell me, if you want to write an equation there, and that equation will contain 3 unknowns, I1, I2, and I3. And another, what is the coefficient A11? What is the coefficient the first element of this matrix, A matrix?
R1.
Sorry,
R1, sir.
only R1.
Sir, if we apply the KVL equation, then it shouldn't it be like I1 R1 plus sorry, minus I1 R2
minus R1, R2. If you apply your KVL, then you will E equal to what? E is equal to I1 into R1 plus I R1
I1 minus
R2 minus what? What will be equal to what? This is equal to R1 plus R2 into I1 minus I2 into R2, isn't it?
Yes.
Yes, sir.
Then what will happen? Then this coefficient will be equal to R1 plus R2, and this coefficient would be equal to minus R2. And what is the coefficient here? Is there any
That's zero.
contribution directly connected between
No,
node
sir.
1, loop 1 and 2? This will be equal to 0, isn't it?
Yes, sir.
Yes, sir.
If you want to write for I2, then what will happen? This should be equal to your what? R2. Then this diagonal element would be equal to what? This is not R2, this is R4. Okay, this is R4. And this diagonal element will be equal to what? Minus R4. This will be equal to R4 plus R2. And this element will be equal to minus R5, isn't it?
Yes, sir.
And your third element, you can easily write that this will be equal to 0, and that will be equal to minus R5, and this will be equal to R5 plus R3 plus R6.
Yes, sir.
And in the right hand side, you will see that you will have your E only there, and others are
Zero.
0. Now you see that in the simple 3x3 network, for this reason you see that you have your something there, but still you see that that matrix has a nature. You see that you have a diagonal main, then you have your two other diagonal, isn't it? And these things are 0. This type of nature of the matrix is called banded matrix. And another issue is that when you are increasing your number of loops, you will see that many elements will be equal to 0. The loop that is not related to any other loop will have no relationship with that. This is the mutual element, okay? Those mutual elements will be equal to 0. As a result, this matrix will have many zeros. And the matrix with many zeros has a name. Do you know what is that name? Didn't you learn it in your power system? Because power system matrix has this type of nature where you have studied your Z bus and Y bus, isn't it?
Yes, sir.
What was the what particular nature you observed in these two matrices? Are not those matrices are many zeros? Those matrices are a sparse matrix. This sparsity of a matrix actually is computation. Sparse matrix is always computationally efficient. The reason is that many zeros will be there. So if you use your conventional technique, they are storing, then you will be using the what we call precious computer resources by for storing zeros. For this reason, some improved algorithm are there just to apply this thing. In this case, direct method are rarely used. The Gaussian elimination technique, even Gauss-Seidel method can be used there to solve those type of sparse systems. Now I will be telling, okay, some discussions are there at the beginning of chapter 12 about this issue. You try to revisit it to get accustomed to some other properties of this sparse system and how Thomas algorithm is used to solve the sparse system. This is very simple, a simple version of your Gaussian elimination technique. Now we will be dealing with the other properties of our Gaussian elimination. Gauss-Seidel technique, that is very important because you see Gauss-Seidel method is iterative method. So if we are using iterative method, then the convergence issue is a factor. Okay, sometimes your equation may diverge. If your equation will diverge, then you have to set your, because you see what have we done earlier. If we have a matrix x1 plus a, I am not writing all the way, just for your time constant. What I am doing that the first equation of the general 3x3 equation is solved for x1. That x1 is equal to b1 minus, what was it? B1 minus A12 divided by A11 into X2 minus A13 divided by A11 into X3, wasn't it? If we solve equation 1 for X1,
Yes, sir.
and if we solve equation 2 for X2, it will be equal to B2 minus A21 divided by A22 minus A3, A, is it A21? X2, yeah, A32 divided by A22 into X3. And if we solve for X3 from equation 3, it is equal to B3 minus A31 divided by A33 minus A32 divided by A33. Is it okay? X2, it is 32. A21, A22, A23. This is not something like this, okay? Now you have your three equations there, X2. This is your X1. What is it to with it? X1, isn't it? Okay, if everything is okay, then what will happen? We start with an initial value X0, X2 0, and X3 0. Then we calculated the next value X11, X2 1, X3 1. In Gauss-Seidel method, immediately calculated value is used for the next iteration, next equation. Okay. For example, say if you want to write a general algorithm for this thing, then you can write that your X in this equation, it will be equal to say Xi, I plus 1, the ith iterative value would be equal to B1 minus you are using, say, this is your ith iterative value. This is also your ith iterative value, isn't it? But if you want to find ith iterative value of X2, then we will be using X1 that we have calculated earlier. It will be equal to I plus 1, the iterative value. This is your ith iterative value, isn't it? And X3 I plus 1 would be equal to what? You will be using the ith iterate already with you. This is also with you. Okay, that means we are using already available values, the current values in this equation. This is your Gauss-Seidel. If we want to use, for example, if we do not want to use it, then the method becomes Jordan method. So in this case, what you can do, you can easily say that if, for example, your successive values are diverging from your solution, because your error criteria should be set that for each of your variable. That means you have your ith iterative value calculated, you subtract it with your ith, and you divide it with your xi into I plus 1. That will give you the approximate error for variable 1. And you can also find your same error for variable 2 and variable 3. A global error specification can be there, so that if the error falls below this level, then you can stop your calculation. Sometimes one variable may just approach faster to the solution than other, but the error criteria should be applied to the variable with slower convergence. This is the conventional way. But the problem is that this will be a diverging situation, will be there. That situation is described in your book very nicely in chapter 11. You try to go through it, how the slope of the curve will affect the speed of convergence of your equations. Okay. In general, the diagonally dominant system is usually very efficient for Gauss-Seidel method. Diagonally dominant means what? If we have our equation, that equation we can be put into the matrix form, and your diagonal element is magnitude of the diagonal element is higher than of diagonal element, then those systems is called diagonally dominant. If we have a diagonally dominant system, and you see that the resistive network that we discussed earlier, Is it a diagonally dominant? Hey, have not you solved any of this type of problem by using matrix in your earlier learning? No. Okay, can you apply the common sense there? That which of the element will be higher, with value magnitude is higher than other? Are not those the diagonal?
Yes, sir.
So your diagonally dominant system is actually eventually will give you a better result that is described in this text. Equation 11.10 is the condition for your diagonally dominant cases. And in such cases, you can have your equations there that maybe they cannot, sometimes your equation in its original form may not be in the diagonally dominant case. In that case, what you can do, the partial pivoting or pivoting that we use, you can rearrange the equation in such a way that your diagonal element will be dominant. And if they are dominant, then only when you can produce a solution, okay? And in such cases, what you can do, this rearrangement of the equation will result in solving for the variable that solution. For example, from equation 1, you can solve for x1. Even you can solve for x2. From equation 2, you can solve for x3. For equation 3, you can solve for x1. In this way, you can go, because this rearrangement will never change the solution. But in iterative cases, sometimes your solution may diverge. This situation depends on the slope of your lines and the initial value and the order you are placing your equation, okay? This is there explained in this figure, okay? You see that in your figure A, if we start from this location, this diagram is called cobweb. In cobweb diagram, you see that if we have our equations there, we are starting from this point, you are going here. So this will intersect at the first line for first equation here, for example, say. Then this is the value that you are obtaining. Then you can project this value in the second curve that you are obtaining this value. Again, you can project it there. In this way, you will see that you will be arriving at the solution. But if you just rearrange, go in the reverse way from in this direction, say you are going in this direction and intersecting here, you will find another value there. What is the difference between these two? In this case, you see that you are using your first equation for your first iterative cases, but in this case, you are using your second equation for your iterative cases, okay? So in this case, if you go in this direction, you see that your solutions are diverging, okay? You can easily observe it by using a simple RL network or a simple resistive network. Okay, in order to investigate this thing, let us use an example, and you just ready with your calculator. If okay, because in general, okay, because it is now in online, but in general, in my class, okay, I never allow a student to come without calculator. But here, probably many of you are not engaged to the extent, but I will never force you to do that. You feel the responsibility of by your own. Then you will feel the importance of learning. Look, we have a system of equation, for example, say 3 into x1 plus 12 into x2. I have given a reference to you in your textbook. You try to explore those references also for further understanding. Okay, your equations are given in this form. Are your equations set in your diagonally dominant form? Because here in your A matrix is equal to -3, 12, 10, -2 into x1, x2 is equal to 9, 8. Diagonally dominant means this. You have to check the diagonal dominance of this matrix A. Is that matrix is diagonally dominant? What is the diagonal?
Minus
Is it
3,
not?
minus
It is not the diagonal.
Yes, sir.
Does it satisfy the condition that you have seen earlier? That the magnitude of these values are higher than other up diagonal values?
No, sir.
That means this equation is actually not diagonally dominant. Now I am telling you, apply your Gauss-Seidel method here with initial value x1 equal to 0 and x2 equal to 0, and try to solve this equation. Next class, I will ask you, everyone. Okay, you solve this equation and try to understand whether you are able to find the solution in the conventional way or not. Then let me know that the result, okay? And if you're converging, then how many iteration will be needed? You first try to solve the exact solution, then you compare the exact solution with the iterative values. How many, if it converges, then how many iteration are needed? And if it diverges, then what to do? Next thing is that if we want to make it diagonally dominant, how can we do that? If we just swap that equation in this way, okay, you bring that equation there and swap this row. That is what that means. You are just simply swapping the position of the equation. Okay, you write the equation in this way: 10x1 minus 2x2 is equal to 8, and minus 3x1 plus 12x2 is equal to 9. In this case, your new matrix is equal to what? 10 minus 2 minus 3, 12, isn't it?
Yes, sir.
Is it now your diagonally dominant?
Yes, sir.
Yes, sir.
It is now diagonally dominant. Okay. Now another issue is that this is one thing, because in this example, I want to show you two important issues. Another important issue that I discussed earlier, actually, in your Gauss-Seidel technique, I don't know whether you applied in your power system or not, but this is the most important issue in your power system engineering. The thing is that when your system will be converging very slowly, or even sometimes it may oscillate between two solutions, what you can do, you can relax your variable in such a way so that your solution will be going faster to the desired solution. In this case, we use a technique, this is called successive over relaxation. And this is described in article 11.22. 11.22, try to have a look. The equation is something like that. In this case, you see that when we obtain a solution from an equation, then we are using the same solution, this immediate solution to the next for solving the next variable. But without using your present solution as it is, a weighted average is actually made. For example, say we have our x ith value. This is the new value. That new value is modified in such a way that it is multiplied by a new value. That value new multiplied by 1 minus lambda into, say, ni xi old. Xi old. This is what the new value you are calculating, and this is the old value. This is some sort of weighted average, and that lambda is called relaxation factor. If the value of your lambda is between 0 to 1, it is called under relaxation, and if the value is equal to 1 to 2, it is over relaxation. And that value of lambda actually problem specific. It is usually determined empirically by solving many problems. In your power system, your problem sometimes you use the value of accelerating factor lambda is nearly equal to 1.4 to 1.6, and you see that your solution will be converging faster. Okay, then how this can be implemented? Let us solve this problem for the example that we have shown there. Okay, I hope you have your calculator with you. Okay, so if we arrange the equation in this way, then you solve for x1 from equation 1. Then x1 equal to what? 8 plus 2x divided by 2x2 divided by 10, isn't it?
Yes, sir.
Yes.
Okay. Then what about your next value, next solution, x2? Your x2 equal to what? 9 plus 3x1 divided by 12,
12.
isn't it?
Yes, sir.
Okay. Then you start your iteration. You can form a table, okay? That your first solution x1 is equal to 8 plus 2 into x2 divided by 10, or you can write it 0.8 plus 0.2 into x2, and your x2 is equal to 9 divided by 9 plus 3 x1 divided by 12 is equal to 0.75 plus 0.25. 0.25 into x1. Start with your initial value x1 0 equal to 0, x2 0 equal to 0. Then what will be the solution for x1? First iterative solution.
0.8.
Is it not equal to 0.8?
Yes, sir.
Now, in our conventional technique, what we usually do that in finding our x to 2, we are using these immediate calculated values, and it will be equal to 0.75 multiplied by 0.25 into x2, isn't it? x1, 1. And that was equal to 0.75 plus 0.25 multiplied by 0.8 is equal to 0.75 plus 0.2 is
0.95.
equal to 0.95, isn't it?
Yes, sir.
But if we want to use our accelerating factor here, then what will happen? Consider that the lambda value equal to 1.2. Then what you need to do, you have to then, okay, without directly using the x2 value here, you have to use a x1 new value. That will be equal to what? That will be equal to 1.2 multiplied by the value that you calculate, multiplied by the old value of x11. What is the old value of x11? Old means we have only two values available with us, the current value and the previous value, isn't it? So the old value is equal to 0. Then this is equal to 0. Then eventually you are obtaining a value of new value. That new value would be equal to what? 0.96. A calculator asana. Now using your 0.96, you the value x2 1. That x2 1 equal to what? This is now SOR, okay? Successive over relaxation. The next two value would be equal to what? 0.78, and that is equal to 0.75 plus 0.24. You understand the thing? And is equal to 0.9. You got the logic? Hey, are you there?
Yes, sir. Sir, your voice is distorting a bit, sir. Therefore, I'm missing your
All
instruction.
are hearing my distorted voice?
Yes, sir.
Yes, sir, it's fading.
Sir.
And it is you can see what I am doing. You see what I am doing.
Yes,
Yes,
sir.
sir.
If you can see if you can see this right up, can you proceed for your next iteration?
Yes, sir.
Do that. Because now your relaxed value for your x 1 is equal to what? Relaxed value that you obtain 0.96, and the relaxed value of your x2 you have to calculate. Okay, that relaxed value would be equal to what? The value that you calculated. There, these two second run value is available with you. Then you use you repeat the same technique. repeat it. Okay, and you see that how fast you can obtain your solution. Okay, so if we have our network issues, probably because in my home, then I have to finish at this point. Next day we will be starting our curve fitting technique for our problem. Okay, you understand what is your task? Am
Yes, sir.
I?
Can you repeat again? Can you explain the task?
Okay, in your first equation, we used a conventional technique first, okay, without relaxation. Then you try to understand that how many iterations are needed to converge your solution. And later you relax the variable in a way that I do with that I have done with lambda equal to 1.2, then compare how these two strategy is converging to the true solution, okay? So that's it for today, because if you have your network issues that I cannot actually resolve at this point, I have my fastest network with me, but it's still we have problems. Okay, you can stop your recording now. I will be giving percentage.